So in the last part of Chapter 8, Handout 2, what we're going to do is we're going to start to look at benzene derivatives. So this means molecules that have something on the ring in addition to the just to the benzene. And really what we'll be looking at is resonance in these derivatives and how we can correlate that resonance with the specific reactivity of the benzene ring. So normally, right, if I just had benzene and, for example, we said we were going to treat it with bromine in the presence of the iron 3 bromide catalyst, then we could just install bromine on any one of the positions. They're all the same. But now the question that we're going to want to ask is, if there's already a group attached, what's going to happen? Where is that bromine going to go? Because now not all the spots are the same, right? There's the spots adjacent to the group. Those are identical to each other. There's the spots 2 away from the group. Those are identical to each other. And then there's the spot 3 away from it that is also unique. So that's what we want to think about here in terms of how an existing group on the benzene ring is going to affect the reactivity. So the next thing we can talk about is di-substituted benzene ring. I'm going to say nomenclature, just our fancy word for naming. And so we've kind of talked about this before, but there are 3 options, right? I could have the 2 groups next door to each other. I could have the 2 groups with 1 carbon spacer in between, or they could be completely across from each other. Those are the 3 options, right? They could be neighbors, they could have a space of 1 between them, or they could have a space of 2 between them. Remember, even though we're showing the pi bonds as fixed, we understand in reality that they're cycling around. So if 2 groups are next door to each other in a benzene ring, we say they're ortho to each other. If 2 groups are 1 carbon apart, then we say they're meta to each other. I remember this one by just saying there's 1 carbon in the middle of the 2 groups, so that's what meta is coming from. And then the last one is para, where they're completely on opposite sides of the benzene ring. So that's some terminology that we're going to want to use as we look at this. Okay, so the first type of substituted benzene we're going to look at, not di-substituted, just mono-substituted with 1 group, are benzene rings where there's an electron donating group attached. And we call these EDGs, electron donating groups. So generally speaking, the way we're going to identify these is it's going to contain a lone pair one atom away from the ring. So if we have a nitrogen directly attached or an oxygen directly attached, that would be an example of an electron donating group. So NH2OH, those are kind of our best examples of this. So let's draw some resonance forms. So we'll use, I think we've talked about the name aniline before, but aniline is a benzene ring with an NH2 group attached. So I recognize that as an electron donating group because there's a lone pair 1 atom away from the ring. And so in terms of resonance, I can push that lone pair in, and I can create a space for that by pushing the pi bond out to be on the carbon ortho to this group. So now it's double bond NH2 plus, and then on the neighboring carbon, now I have a localized charge, and so there's a negative charge there. So here we have the negative charge ortho to the attached group. Then I can kind of regenerate that pi bond in the neighboring spot, and then scoot the neighboring pi bond to be localized on now the para-carbon. So we still have NH2 plus at the top, but now we've got this negative charge at the para position. I can do this one more time, right? I can bring that lone pair back in as a pi bond, and now localize the other pi bond in the other ortho position. So what we want to say about electron donating groups is it, in general, in general, EDGs add electron density to the ring. That makes sense based on the name, right? It's donating electron density. But specifically, EDGs add electron density ortho and para. So it makes the benzene ring more electron rich in general, but it specifically makes the ortho and para positions more electron rich. So remember, when we're talking about electrophilic aromatic substitution, benzene is the nucleophile. So having an electron donating group is going to make a benzene ring a better nucleophile in general, but it's going to specifically make it a better nucleophile from the ortho and para positions. So what does that mean in terms of our reactivity? Well, if I'm starting out with aniline as my reactant, because it's an electron donating group, it's going to make it particularly easy for the bromine to add ortho or para. So when I run this reaction, I'll make one product where the bromine adds ortho and another product where the bromine adds para. But I won't make a product where the addition occurs meta. And our rationale for that we talked about is that the benzene is specifically electron rich at the ortho positions and the para position. And the two ortho positions are identical, right? So I don't need to draw the product on both sides because these are all sp2 carbons, so it's going to be the same product regardless. So that's an added piece of information, right? Now when I identify a molecule with an electron donating group and it's going to undergo an electrophilic aromatic substitution reaction, I know that I'm exclusively going to form the product where the addition is occurring ortho and para. So I should get both of those products. So this would hold true regardless, right? If I were doing a Friedel-Crafts acylation, it would work the same way as well. So if instead we did our Friedel-Crafts acylation, then again here, the expected products would be the ortho and para addition of this group. And we could get into more detail, right, and figure out which one is more favored. And there's a lot more to talk about with regard to the reactivity of benzene, but at this stage, this is a reasonable way to look at all of this. So far we've been talking about electron donating groups, but you could imagine that we could also be talking about electron withdrawing groups. So these are EWGs. Let's see, let's go up here. I said lone pair, one atom away from ring. Now we're going to say pi bond in conjugation, which means it's adjacent to with benzene ring. So this could be a ketone or an aldehyde. This could be an ester, an acid. It could even be an alkene. These would all be things that we would consider to be withdrawing groups. We could even have it as an alkyne. These would all be withdrawing groups. So you can imagine we're going to sort of see the same thing in reverse, right? So an electron withdrawing group is going to pull electron density from ortho and para. So we'll see that it generally reduces the electron density, but it specifically pulls from the ortho and para positions. So it looks like I use benzaldehyde as my example here. So think about what we know about resonance, right? If I came to this molecule and didn't know what else to do, I could certainly push the pi bond out from the carbon to the oxygen. That's kind of our go-to first structure. And that would effectively create a plus charge vacancy 1 carbon away. So now we can scoot the pi bond out from the ring. I guess I'll stick with red now. Out from the ring. And now, rather than creating an anion inside of the ring, we're going to create a cation inside of the ring. And now that cation can be distributed using the pi bonds we already have in the benzene ring. So I can scoot the pi bond over and now we have the plus charge para, and we can do it one more time and then scoot it to the other ortho position. So hopefully what you can see here is it's literally doing the opposite of what an electron donating group was doing. So now the benzene ring is stabilizing the positive charge, but in doing so, it's putting a positive charge specifically in the ortho position and specifically in the para position. So if we use the same description as we did before, we'd say, in general, electron withdrawing groups remove electron density from the ring. And there's a lot more detail in the handout that you can read through, but I'm kind of cutting to the details. And then specifically, electron density is removed ortho and para. So the way to think about it in this case is to say the ring is less, let's say, nucleophilic overall, right? It's more electron deficient because of the withdrawing group. But the most nucleophilic site is the meta position. So really we're talking about the least bad option, right? We're saying it's not going to be as reactive overall, but if we are going to react, we're not going to react from the ortho and para positions that are specifically electron deficient. We're going to react from the meta position, which isn't being specifically affected. So the example I used here was just with benzaldehyde. The bromine reaction is kind of the easiest. Bromine with iron 3 bromide. And there's only one meta position, right? I know it looks like you could put it on both sides, but that's the same product. So we say we're exclusively less electron poor at the meta positions. So that's where our group is going to add on. And this will be true regardless, right? If I had anything else in that group, so let's say it's a ester, and then let's say we do Friedel-Crafts alkylation, then we'll again say, well, the meta positions are going to be the least electron deficient, and so then we'll get addition of our group at the meta position. So this is one more layer, right? So in addition to knowing what all the reagents do in the electrophilic aromatic substitution reactions, you want to be able to look and say, okay, this group is electron donating, so addition will happen ortho and para, or this group is withdrawing, so addition is just going to happen in the meta position. So again, you're really looking for whether the group that I've attached has a pi bond adjacent to the ring, which makes it a withdrawing group, or a lone pair, which makes it a donating group. Let me just write that down once. So electron donating group, we'll just say lone pair next to ring, and then electron withdrawing group, pi bond, I'm going to say bonds in case it's an alkyne, next to ring. All right, that's really a wrap on the Chapter 8 Handout 2 and Chapter 8 overall. So as you're working through the problem sets here, you're going to want to kind of practice overall what each reaction does, and then specifically being able to classify electron donating groups and withdrawing groups, so you can do these fill in the product type questions. Yeah, so let's go ahead and leave it at that, and that's a wrap for chapter 8. I think the next chapter will be chapter 12, and then lastly we'll have chapter 9, and that'll be our last chapter.